So, I think we could start. Warm welcome to everyone. Good afternoon or good morning, good evening, depending on where you are joining us from. This webinar is being recorded and will be published on our website afterward. However, the chat will not be included into the recording. It's my pleasure to welcome you to this webinar, Solar PV Powered Room Air Conditioning Market Trends and Techno-Economic Potential. Today we will make a deep dive into the update of the 2022 published study on solar by powered room air conditioning. The author, Professor Paul Kulmbach, is with us and will introduce the study. My name is Milan Desanayke and I'm an intern at GCI III and the C42 project. Today I have the pleasure of being your facilitator and guiding you through this event. Let me start with a brief introduction to today's event. This webinar is part of the GCI III recently introduced webinar series, Green Cooling Webinars, which addresses all members of the Green Cooling Network and is co-organized by the C42 project's NDC4 webinar series, which addresses policymakers and highlights the crucial role of the cooling sector in driving more ambitious and enhanced NDCs while promoting comprehensive mitigation approaches. As the C42 project is going to be completed at the end of this month, this is also the last webinar of the NDC4 webinar series. Before we begin, let me share some important technical details. Please keep your microphone muted during the session. If you have any questions, feel free to type them into the chat. We will address them during the Q&A session after the presentations. I'm joined by my colleague, Teresa Bruns, who will assist with any technical issues. If you need help or have individual questions, please reach out to her. You can find her email address in the chat. Now let's test the chat to make sure that everything is working and to get to know each other a little bit better. I have two quick questions for you. Which country are you joining from and what organization institute are you from? Please type your answer in the chat. Yeah, we have Brentwood Tech UK. Nice. Maybe some more answers in the chat. Yeah, we have participation from Sivakamur, India. Nice. From Honduras, Cuba, Australia. Very good. It's wonderful to see participants from all around the world, Switzerland, Germany. Nice. Okay, let's take a look at the today's agenda. We are very pleased to have two main speakers with us today. First, we will begin with opening remarks from Claudia Alvarez, head of the C42 project. After that, Professor Paul Kulmbach is going to provide insights into the new study on solar PV powered room air conditioning. Finally, we will have a Q&A session where we will address any questions you may have. You can post them during the session into the chat if you like, or raise your hand at the end of the session. So let me now give the floor to Claudia Alvarez, head of the C42 project, who will start off the webinar with some opening remarks.
Thank you very much, Milan. Well, ladies and gentlemen, on behalf of GCI Pro Klima, and I'm delighted to welcome you to the webinar on the updated study, the solar PV powered room air conditioning, market trends and techno-economic potential. This event is the last webinar within the NDC4 webinar series that was organized by the project Co-Contributions Fighting Climate Change, the so-called C42 project in the second phase, which comes to an end by the end of this month. but since this webinar is also organized in cooperation with the Green Cooling Initiative and its new series Green Cooling Webinars, our input with interesting topics will continue. The two projects are part of the International Climate Initiative, ICI, and financed by the German Federal Ministry of Environment, Climate Action, Nature Conservation, and Nuclear Safety. The topic, the solar PV air conditioning. Current air conditioning practices significantly contribute to greenhouse gas emissions. And the demand for air conditioning is increasing drastically due to population growth, urbanization, and climate change. The number of split AC units in use is expected to rise from 850 million a few years ago to over 3.7 billion by 2050. So the new study that we will present here is an update to a study that was published in 2022 by GCI III on the topic and highlights the potential of renewable energy sources. The combination of using renewables, energy-efficient air conditioners, and climate-friendly natural refrigerants for a truly green cooling has a great potential to meeting the Paris Agreement. So with the declining costs of solar PV and energy storage equipment and improvements in AC technologies, solar-powered cooling is becoming increasingly viable, both technologically and economically. In this webinar, as Milan already said, we will delve into the technical and economic potential of solar PV-powered green ACs, focusing on single split type air conditioning systems with a cooling capacity of up to 5 kilowatt for residential and small commercial applications. We will discuss hybrid and off-grid solutions and analyze these cases across 17 countries using different electricity and net present value metrics. A case study using ice storage instead of battery storage will also be presented. So this webinar aims to foster further development in the promising yet nascent PV AC market and inspire continued research and practical applications. Thank you for joining us today. I wish us a very successful webinar and fruitful discussions afterward, after the presentation of Dr. Professor Kohlenbach. Thank you very much for your attention, and back to you, Milan.
Yeah, thank you, Claudia. Now I'm pleased to introduce Professor Paul Kohlenbach, who will share the newest insights on solar PV-powered room air conditioning. Paul Kohlenbach is a full professor for renewable energy at the BHT University of Applied Sciences, Berlin, Germany. His research focuses on energy economics, refrigeration technology, photovoltaic, solar, thermal, and hydrogen technology. Professor Kohlenbach is also the founder and owner of Solem Consulting, an international consortium of leading experts in solar and refrigeration technology. There his work focuses on the design and economic efficiency of energy systems of all kinds. Paul is also the German delegate in the executive committee of the International Institute of Refrigeration in Paris. Let me remind you, if you have questions during the presentation, please post them in the chat and we will discuss them in the Q&A session later. Paul, the floor is yours.
Thank you very much for this very kind introduction. Everyone, also a warm welcome from my side. We have an update here for you. A new version, 2025, fresh from the press, of our study from 3 years ago. Let me first introduce not myself, that was just very elegantly done, but also my co-author, Professor Dr. Uli Jakob, who is honorary professor for building technologies at the University in Stuttgart. And together, the two of us run Solem Consulting, as it was introduced just now. What is new in this present version of the study. Let's start with a short view. Back 3 years ago, we presented work on this for 13 countries. We have used some boundary conditions, some assumptions for our modeling and simulations, which back at the time seemed reasonable. But since then, we've had very good feedback, and we've included the feedback on the 2022 study in order to present everyone here an updated version with hopefully more precise results. So what is new in the 2025 study? We've increased the number of countries by 4, included Albania, Brazil, Tunisia, and South Africa as new countries. We have now used individual values for the air conditioner investment cost, which 3 years ago was a constant value globally. We've taken into account the market change in the global PV market, where monocrystalline PV modules have taken over from the polycrystallines, which we have used in 2022. And also we've updated all the other cost values, electricity prices, inflation rates, the PV capex cost, and the country feed-in tariffs for PV generated electricity. So that, in a nutshell, is what we are going to present today. The countries investigated, just for your overview, are shown on the global map here. So you can see we almost have countries on every continent here, included some very small countries like Grenada and Ireland, some very big countries like Brazil and China. We've tried to pick those to incorporate a good sort of part of the global diversity. It was mentioned in the introduction that we have been focusing on small split type air conditioner. And I would like to introduce you now to our framework, so to the methodology that we have used to generate the results. First of all, 2 different systems have been investigated. On the left-hand side, where the red pointer dot is now, you can see the schematic of a house, a building, PV panels on the roof, an inverter to change from DC to AC current. Inside the house, we have some appliances, for example, an air conditioning system. There is a meter for electricity with the combination to the mains grid. We call it a hybrid system because it is grid connected. So the possibility to run all appliances, including air conditioning from grid power, is there, but also we can run it on PV power if sufficiently available. In this concept, there is no battery because the grid serves as a battery. So in case of no sun, we can always run the system on the mains grid. The other system is the opposite. It's an off-grid system with no grid connection. PV panels on the roof, air conditioner, appliances in the house. But in addition, we there have a battery system, a battery storage system to account for times with no solar radiation to be able to run the house and the air conditioner on PV power at night times or during cloudy periods. So those are the 2 technical options that we have investigated. The second degree of freedom that we've looked at is the building type. Both these systems have been applied to a residential building, smaller size, and a small commercial building, slightly larger size. You can see the numbers here for the air conditioning system, the PV peak power system, and the battery size in case of the off-grid options. Further, for each country, we have looked at 3 different locations. The map here shows an example for China, and the measure we've chosen to differentiate between those 3 different locations is the global horizontal irradiation. So that's the amount of energy on 1 square meter per year. We call that GHI. We've chosen 3 locations according to the GHI distribution per country, and we've chosen a location with the minimum GHI, so the lowest solar irradiation, an average one, and the maximum. You can see some example numbers for China. And just by looking at the numbers, you can see that the difference between the minimum and the maximum GHI here is rather significant. Some countries have a big difference in those three numbers. Other countries, not so huge the difference. If you think of an island like Grenada, those three values would be very close to each other. But for larger countries like China and Brazil, it does make sense to make this differentiation. For the modeling, we've done assumptions. We've used assumptions, monocrystalline silicon PV panels, globally available. We haven't chosen the world record holder here in terms of efficiency, but we've accounted for a global average of module efficiency in order to make it a more homogenized value for the whole world. The panels always point due south. Of course, in the southern hemisphere, they will point due north. I forgot to mention that here. And we have an optimized PV panel slope per latitude. In summary, what we've done is we've used 2 building types, 2 system types, 3 locations per country, 17 countries. So that comes to 204 individual simulation runs. So that is the methodology. That's what we've performed here. In order to account for economics, we have looked at 2 different parameters. First, the levelized cost of electricity, LCOE. Some call it levelized cost of energy. It's the same parameter. It's basically a value representing a cost to generate 1 kilowatt hour of electricity over a certain number of years, including an interest rate. The second parameter we've looked at is the net present value. The difference between levelized cost of electricity and net present value is that the latter includes earnings. LCOE is just cost, which is a very useful parameter to compare different systems. But if you want to include earnings from feed-in tariffs, which in some countries are present, then levelized cost of electricity would not take into account the feed-in tariff. And hence we've chosen NPV, net present value, to count earnings from feed-in tariffs where present. You can see the economic assumptions here, 20 years lifetime of plant, an interest rate of 5%. Consumer price index was chosen individual per country. The OPEX cost, the operating expenditure for the PV modules, was chosen at 1.5% of the CapEx per year. And the CapEx, so the investment cost for air conditioning, AC, and PV modules, was also an individual value per country. Throwing it all in, doing the simulation runs, this was the assessment framework. What we wanted to find out was, is it economically viable to invest capital into a PV system, an air conditioner, and, if needed, a battery to provide air conditioning for the building, for either a residential or a small commercial building. So that was the question we wanted to answer. Let's have a first look at results. This is an example for the hybrid technical option in a residential house. So just to remember, hybrid means we do have a grid connection. Residential means smaller size building. What we see on the y-axis here is the levelized cost of electricity. So the currency here is euros. How many euros does it cost to generate 1 kilowatt hour of electricity for this residential building? And we have 2 results shown in the graph. The blue dot is the levelized cost of electricity for the average location, the average solar radiation location per country. So an average location. The red dot is the levelized cost of electricity minus a feed-in tariff. Feed-in tariff can be from, or is usually from the government for electricity that is fed into the grid. And you can see that we do not have red dots in every country. That is because not every country does have a feed-in tariff present. The black bar that is shown, for example, here for Iran, around the blue dot, that is the difference between the location in the country with the minimum and the maximum radiation. So the top end of the bar shows the levelized cost of electricity for the location with the minimum solar radiation in the country. If there is less solar energy generated, then the cost per kilowatt hour is higher. The bottom end of the bar is the top spot in the country, is the location with the highest solar radiation, which then decreases the levelized cost of electricity. To put it all in perspective, the gray bars, the gray columns here, show the net electricity cost for grid power. So that is the amount of money you have to pay per country to purchase electricity from your grid supplier. A first indicator for a successful economic system here is if the blue dot is lower than the gray column. So in other words, the levelized cost of electricity is lower than your net electricity cost. In this case, it's cheaper to generate your own PV power than to purchase from the grid. And we can take Colombia as an example here to show that the location does matter. The average solar location in Colombia is below the net electricity cost. However, the top end of the bar here is above the net electricity cost. So in Colombia, it does matter where you are. Locations with minimum solar radiation generate higher costs. The location with the top solar radiation, the bottom end of the bar, generates lower cost. This is how to read this graph. For countries with a feed-in tariff, for example, if we look at Ghana here, it is visible that without a feed-in tariff, the blue dot is almost at the top end of the gray column. So that means the levelized cost of electricity is almost similar to the net electricity cost, and there would be no real financial advantage. However, taking into account the feed-in tariff that the government pays for solar power, you can see that the LCOE is now almost reduced to zero. And in this case, using the feed-in tariff, the economics really do stack up for countries like Ghana. You can see Grenada. If we subtract the feed-in tariff, we even have a negative levelized cost of electricity. Now, what does that mean? It does mean if you supply excess PV power into the Grenada grid, you get paid for it. Okay, you don't have to pay to purchase, you get paid for feeding in. And we see that some other countries with feed-in tariffs also have a negative levelized cost of electricities. In countries like Vietnam, Iran, and Ghana, the feed-in tariff does reduce the LCOE cost. However, a small fee still is to pay. So this is the result shown for a hybrid residential system. So the smallest unit that we have looked at, a grid-connected unit in a residential house. We have provided these graphs in a similar way for the three other combinations: for off-grid residential, so we're using a battery; for commercial buildings in the hybrid version, same as this, but for a larger building with a different load, I have to mention, and commercial off-grid. So if we have a commercial building with a battery storage, not grid connected. For reasons of time here in this webinar, I won't go into details with all four technical options. Rather, I think I stay with the hybrid residential system and show you the results for the net present value. LCOE, like I said, does not take into account any earnings. The net present value does. We all know we have to pay for air conditioning, right? It doesn't come for free. Anything we want to chill below ambient temperature is going to cost us money. And the question is how much? The net present value in this case, shown on the y-axis here, as you can see, has almost everywhere as negative figures. And so that means we always have to pay for air conditioning. In some countries, we have to pay more. In other countries, we have to pay less. Blue dots here represent the net present value in the PV version for the residential house, that is, without a battery, grid connected. Now the orange dots here, they do not represent any feed-in tariffs. In this case, they represent the base case. Now, what is the base case? If you are a building owner, you usually have a few choices if you want to install air conditioning in your house. And the base case that we have chosen is just a stock standard air conditioner with R410A as a refrigerant that you can purchase off the shelf, install it in your house, no PV power, and you just use grid-connected power, grid energy to run it. So this is the base case. And this would attract a cost that depends on your local net electricity cost in the country you're in. If the blue dots, which represent the same number, but for an air conditioner that is PV driven, if the blue dots are above the orange dots here, then we have a smaller cost over the lifetime of 20 years than with the base case. And if we look closely, we can see that in the green marked countries, the green air conditioner running on PV power is actually economically feasible because the cost in the PV version, the blue dot, is above the orange dot. So we pay less for the PV option, even though we have to install additional PV modules, which obviously incur an extra investment cost. There are only two countries, Iran and Tunisia, where this is not the case. So in both these countries, the base case is cheaper than the PV option. To a small extent, one could argue, but if you take the numbers seriously, which we do, then we have to say it is not economically feasible to operate a green air conditioning system with PV power in those two countries. But in all others, it is. So these results you will find in the study for the three other options as well. If there are specific questions on the three other options, I have those slides as backup for the Q&A part later, but for reasons of time, I think I should move on. An overview without the details is given here. You can see the four options: residential hybrid, residential off-grid, commercial hybrid, commercial off-grid. And I have tried to make a differentiation for on the economics here. The best result that we can achieve is if we virtually do not have any cost over the lifetime of 20 years for the PV air conditioning. So that's the three pluses. And you can see Grenada in the commercial hybrid version virtually has no cost due to the high feed-in tariff in Grenada, I should add. Thailand, the same. In Thailand, commercial hybrid operation is possible at no lifetime cost. Two pluses means the net present value of the green air conditioning version is higher than of the base case scenario. So that is still economically feasible, but there will be costs over lifetime. And one plus is the net present value is in the sensitivity range of the base case scenario. So that means if you see a single plus, that means it really does make a difference where you are in the country. If you are in a location with good solar radiation or in a location with bad solar radiation, that does make the difference for the countries with a single plus. Countries with no plus at all, like Iran or down here, Tunisia, means it is not economically feasible to run the green air conditioning. So that's the results of the assessment framework in a nutshell. Like I said, any questions on details we can discuss later. I'd like to move on and present you one alternative option that we've also investigated, which is ice storage. I said before that 2 of our technical options included battery storage in the off-grid versions. Now, we all know batteries are rather expensive. I've put back here the schematic of an off-grid powered PV air conditioning system for a building. And battery cost can sometimes be prohibitive for economic operation in those systems. So the question we wanted to answer is ice storage for 24/7 AC operation, so day and night, technically feasible as a substitute for the battery? We've done a technical assessment here, I should add. We haven't done the economics yet. There was no time to do that in this update of the study, but at least we looked at it from a technical point of view, which is always a start. So in our schematic, this one here shows the PV option. So let's take out the batteries. If we use PV panels through an inverter, we can run the air conditioner, but only if the sun is shining. If we want to add storage, we have to slightly modify our air conditioner. And we have to use something like this. This is just a concept which wasn't developed by us, but by others. And this concept does include an ice storage tank. Let's start from left to right. We have a conventional outdoor unit here, which is powered by PV electricity. This outdoor unit would normally be connected straight to the indoor unit, which is labeled with a small d here. But in our case, we have connected an ice storage tank in between. And the idea here is to run the indoor unit at nighttime on stored energy from the ice storage. To do so, we would use the purple circuit here, a small pump, and the circuit is filled with glycol and water, so we can go to lower temperatures without the water freezing. If there is sufficient ice in this ice tank here, then we can just run this glycol water loop and provide cold to the indoor unit. To do so, we need to freeze the water in the ice storage tank, and that we have to do during daytime when the sun is shining. And for this, our outdoor unit is modified. It does run on a natural refrigerant here, shown in the green circuit, R290. So propane was the refrigerant we have used here. So at daytime, the outdoor unit, powered by PV power, provides temperatures below 0. The heat exchanger, labeled B, takes away the heat from the ice storage, and we can freeze the water during the day. That is the general technical concept here. So we use excess PV power during the day to freeze water, and at nighttime, we just use the stored energy in the ice storage tank to provide cooling air conditioning to the house. Some boundary conditions. It was done for a location in South Africa. You've got the coordinates here. We have chosen a cooling capacity of the air conditioning unit of 2.5 kilowatts. Peak power was 1.5 kilowatts. There was no grid connection. All the energy used for air conditioning is from the PV panels. And we've just used an ice tank of 216 kilograms of water, which equals 20 kilowatt hours of thermal energy stored. And that is just enough to run air conditioning all night for this building in South Africa. So these were the assumptions and the boundary conditions. To include the climate data, we have combined climate data with the air conditioning load calculation of the building. What you see here is 8,760 values of ambient temperature at the location Makado Airport in South Africa. Every blue dot is an hourly value of ambient temperature. And we have said that we will have a threshold temperature, marked in orange here, of 21 degrees. So if the ambient temperature is above 21 degrees, that's when the air conditioning starts, and it ramps up to its maximum capacity depending on the ambient temperature. If we then look at all the blue dots that are above the orange line, which is shown in the blue area here, then we can conclude at this location in South Africa, we have 3,863 hours per year of air conditioning in operation. That's a total of 161 days. And if we express it in thermal energy, it's about 5 megawatt hours that we have to remove from the building to provide air conditioning. So that was the air conditioning load calculation. Let's have a look at results from the ice storage. What we see here is basically an overview of the system. We have the PV modules, inverter. We then run AC, electrical energy, into the R290 air conditioner. That's the outdoor unit from the previous slide. Here we convert electrical energy into thermal energy. Some of it goes into the ice tank. That's the way down here. And some of it goes directly into the air conditioner. Of course, during the day when the sun is shining, we can run the air conditioner straight off the PV panels. The building load in total is the 4.9 megawatt hours, the number given up here. So if that equals 100% of air conditioning building load per year, then we can see that the combination of direct air conditioning operation and nighttime operation of the ice storage comes to 92% of this annual building load. So only 8% of the annual building load cannot be covered because there is no sun and the ice storage tank is empty. 92% of the annual building load can be covered either by direct operation or by operation via the ice storage tank. You know, nothing goes without losses. If you have an ice tank somewhere in a hot climate, some of it is going to melt. The thermal loss equals approximately 1.6 tons of ice per year, which in contrast to the generation is a fraction, because the ice mass generated over the year is more than 13 tons. We also have some unused electrical energy. In a system without grid connection, we cannot do anything with this. We cannot feed it into the grid. It is simply not used. In a grid-connected system, obviously, something could be done with it. Here, it has to be considered a loss. So this is a result for one specific combination of PV modules and ice tank capacity. Now, of course, we have chosen those boundary conditions. And the question that arose was, well, can we get those 92% up to 100? And what have we got to do for it? So we've done a sensitivity analysis. This table shows you on the horizontal lines here, we've got the ice storage capacity expressed in two ways, in kilograms of ice or water, and the corresponding thermal capacity. So you can see that from left to right, the ice tank size here is increasing. I've plotted the solar fraction. This is the percentage of building load that can be covered by running on PV power. The conditions that we have used for the previous slide are marked red here. In the first column here, I call it the level of comfort. It's basically the temperature from which on air conditioning starts. And in the present study, we've used 21 degrees. If it's hotter than 21 degrees outside, we start the air conditioner. We could say 22, 23, we could even go up to 26. That would mean it's a bit hotter in your house. The level of comfort may decrease. but it doesn't have an effect on the overall system performance. Now, what can we see? The 92%, the result from the previous slide, we can find here in the cell. We can increase those 92% to 100 if we go further to the right. We increase the ice tank size, and certainly with a big enough ice tank, we can achieve 100%. On the opposite, from the 92%, we can lower the level of comfort a tiny bit and set the cooling threshold temperature to 23 degrees, and it will give us 100% of coverage of the annual building load. Solar fraction is maybe something that not everyone is familiar with, so I did plot this table in a different sort of currency, so to speak. Shown here is the same ice tank size versus cooling threshold temperature, but expressed in hours per year without air conditioning coverage. So the 92% we've had before corresponds to 167 hours per year where you would be sweating inside your house. And if we reduce those numbers to 0, then we don't have to sweat, we don't have to feel uncomfortable in the house. We can always cover the air conditioning load. So that's how to read this table. Like I said before, we didn't do an economic calculation for the ice storage. That may be yet to come in a future update. I don't know. Let's come to the summary and conclusions. For the assessment framework, that is the 17 countries, etc., we can conclude hybrid PV-powered air conditioning has a financial advantage over grid-based air conditioning in almost all countries, 15 out of 17. The exceptions are Iran and Tunisia. Off-grid powered air conditioning, because of the higher cost for the battery, is feasible in 10 out of 17 countries, with the exceptions of China, India, Iran, Senegal, South Africa, Tunisia, and Vietnam. If we go to the larger building, small commercial building, it gets even better. The hybrid option, grid connected, has a financial advantage over grid-based air conditioning in almost all countries. Here, the only exception is Iran. So 16 out of 17 countries, the economics do stack up. Off-grid, same number, 10 out of 17. Off-grid commercial, the exceptions are slightly different to the ones above. China, India, Iran, Senegal, Thailand is now here in the list, Tunisia and Vietnam. Let's conclude on the ice storage. For the snapshot study that we did, which, just to remind you, was a storage tank of 216 kilograms and a 21-degree cooling threshold temperature, we can conclude 92% solar fraction was achievable. That number is composed by 69% covered through direct PV operation, 22% from the ice storage, and 8% cannot be covered. The sensitivity analysis that we have conducted basically tells us we can achieve 100% of solar fraction, and I've plotted the two extremes here. If we want to keep the cooling threshold temperature of 21 degrees, we need half a ton of ice, basically. If we don't have such space for that much water or ice, we can reduce the ice tank capacity to 86 kilo, but then we have to live with slightly warmer temperatures in the house and a cooling threshold temperature of 26 degrees. However, various combinations of both parameters are possible, like we've just seen. The 100% can be achieved through many different combinations. And that takes us to the end. I thank you very much for your attention. The study will be published soon. You will be sent the link, I suppose. The slides here will also be made available after the presentation. And I think it's now time for questions. Thank you.
Yeah, thank you very much for the interesting input, Paul. If you would like to delve deeper into the study, like Paul said, you can download it from our website in the next days. Now that we have explored the new insights and findings of the study, I am sure many questions have come up. Now is the time to ask them as we are starting with our Q&A session. Please, like I said, post your questions in the chat or raise your hand. Okay, we have our first question from Daniel, which is, what humidity in percentage, relatively humidity, did you calculate with, Paul?
Yeah, thank you very much. Very good question. Of course, air conditioning load in a building is composed of sensible and latent loads. We basically had to make it a bit simple here. We had to assume that the air conditioning load in the building is not a function of the actual humidity climate data. That would have made things much more complicated. What we've done is we've used a load distribution of the total air conditioning load. So that is latent plus sensible in an annual hourly variation, which was individual per country. But we did not differentiate between sensible and latent load. It was a total AC load.
Okay, thank you for the answer. Do you have any more questions in the chat to Paul? You can also raise your hand and speak up how you like to do it. Any more questions at the moment? Otherwise, I would say, Paul, everything is answered before. But here another question is coming in from Nigel. The question, was all the ice generated by the cooling circuit?
Yeah, thank you for this question, Nigel. Indeed, so the concept we did model was that during the day, solar power generated from the PV modules goes two ways. It goes directly into the in providing air conditioning operation for the building, and excess power was used to freeze water in the tank. So all the ice that is generated within the tank is originally the heat removed is via the cooling circuit. So in short, the answer is yes to your question.
Okay, thank you, Paul. There we have another question from Odie. What were the specs of the solar panels?
Yeah, very good question. We, like I said, we have. Excuse me, where are we? Okay, here. Sorry, I was looking for the slide. We've used a global average value, or we hoped that it's sort of representing a global average value. So it was monocrystalline PV panels with an average annual efficiency of 16.4%. And a module area of, I think, 4.9 square meters per kilowatt peak. So that is, to my knowledge, that is a representative value for the global sort of distribution. It's not a top panel, but I think it's an average value on the market.
Okay, thank you. We have another question from Michael, which is, what was the operation temperature minimum and maximum of the ice storage? Yeah,
also a very good question. We did not model the ice storage tank on an hourly basis with the exact spatial distribution of the temperatures. So basically, we used the heat of fusion to calculate how much water can you freeze in what time if you have such and such cooling energy available from the R290 circuit. So that level of detail to go into the ice storage tank, that wasn't possible in the scope of this study. It was done on an energy basis.
Thank you very much. We also have another question from Siva Kumar, which is, can you please inform whether we can go lower temperature of the room to 15 degrees?
Yeah, thank you. In the combination with an ice storage tank, the ice obviously has a temperature of 0 degrees. To freeze water, we need to go below 0 degrees. And so in this secondary circuit, the purple one, if you remember, we certainly can have temperatures below 0. And then it's a question of the operation of your indoor fan coil unit, what the room temperature is. But technically, it's certainly possible to go lower than 15 degrees, provided the building does have a certain sort of building envelope, and is not just a tent or something where the heat removed is then transmitted through the walls at the same rate. So for a standard sort of, let's say, clay or brick or even wooden insulated building, we should be able to go lower than 15 degrees, yes.
Okay, thank you. Mary has another question, which is, what was the rated panel output power? What was the peak sun hour value used?
Yeah, the rated panel output power was depend on the building type. So we have 1.5 kilowatts and 2.5 kilowatts depending on the option for the residential and commercial building. And the sun hour values, I don't know, do you mean the number of sun hours per year? We did not calculate that. What we did model was the actual electricity output that the panels generated per year. We didn't do the sun hour calculation. We rather went for straight electrical output.
Okay, Mary has another question, which is, did you consider a capacity multiplier for the ice storage?
Would you be able to explain what you mean by a capacity multiplier? Does it just mean multiple ice storage tanks, or what do you mean by that?
Mary, do you have maybe another explanation for your question?
Feel free to switch on your microphone and we can discuss it.
That would be possible as well.
Hello, so this is Mary. For the capacity multiplier, so when considering the kind of ice storage you're using water with LCOE. In most cases, it's not 100% efficient. It usually covers maybe 70% or between 65 and 70% of the capacity for ice storage. So was that put into consideration when making the calculations determining the tank size?
Okay, yeah, now I know what you mean. Running a low temperature coil through an ice tank does not sort of mean you transfer the complete amount of energy, and you also have obviously a limit to the ice formation. In this storage, in this simulation, we did not consider a capacity multiplier for the ice storage. Like I said, it was just done by using energy transfer through the latent heat of fusion. So the answer to this question is no, we did not.
Okay, Mary, I hope that explains it for you. I think that was also the last question here in the chat. I would say thank you for the interesting questions from all the participants. And unfortunately, our time is almost over. Now I'll give the word to you, Claudia, for some closing remarks. Thank you.
Yes, thank you. Thank you very much, Paul, for this presentation. I think it's quite with all the formulas you put on the screen and explain it so well. So thank you for these insights. And yeah, for me, it's time to say goodbye. This was the last webinar in this NDC4 webinar series, and it was a great time to have you here. And we will keep on doing other webinars in another format. So thank you very much for staying with us today and all the last webinars as well. It was a great pleasure, and yeah, stay tuned. We will inform you about the next upcoming webinars within the Green Cooling webinar series. Okay, thank you very much. Back to you, Milan.
Thank you. Bye-bye.
Yeah, thank you, Claudia. Now, as a reminder, the CIFOR2 project is coming to an end, but not without having provided many tools and publications such as today's. We invite you to visit our website, greencoolinginitiative.org, and have a look at the selection of our tools, include a variety of tools to enhance our NDCs with the cooling sector, for example, the CIFOR2 NDC guideline for the ARC sector, or a mini module series to better quantify HFC emissions. Additionally, you can find many interesting publications and studies on green cooling in our green cooling library. You can find the links in the chat, and we would be happy to support you in the future. However, as I said in the beginning, this webinar is the last webinar organized within the NDC4 series, but it is also organized by the GCI III project and part of the Green Cooling webinar series. Therefore, some more webinars will follow, and we are happy to provide you with more insights into green cooling. We hope to keep in touch and see you at the next Green Cooling webinar on 16th June on new publication on green refrigeration and air conditioning in the hotel sector. We will share all the information soon. With that, in the name of GIZ ProClima and the speakers, I would like to thank you for your participation. Thank you again. Take care and goodbye. See you soon.
Thank you. Bye.
Bye. Thank you very much.